Hi everyone, my name is Paras Chopra and today I'm with Professor Lee Cronin. He's a Regius Chair of Chemistry at the University of Glasgow in UK. He's interested in the intersection of computation, life and chemistry. His research group is trying to recreate life from scratch by mimicking the atmospheric and terrestrial conditions of the early Earth. In his pursuit of figuring out how life arises, Professor Lee Cronin has ended up pushing chemistry to its limits. The most recent manifestation of which is the computer. It's a computer that can be programmed to synthesize almost any chemical you can imagine. Unlike many other scientists who study the origin of life, he's unique in his approach in trying to study life from its inorganic precursors. That is, he wants to find out how can complex organic molecules that life needs can evolve from inorganic molecules that get formed in the core of stars. So today we talk about the origin of life and how we might end up finding it and a lot of other interesting topics. Welcome, Professor Cronin.
Hi, it's really a pleasure to be here. Look forward to the conversation.
Fantastic. So I wanted to start by understanding your background. How did you become interested in trying to find out how life was started? I was reading in your bio, you became interested in it when you got your chemical set and a computer at the age of 8. But I'd love to hear from you. What did this evolution as a researcher studying the origin of life look like for you?
Yeah, I mean, I never really realized that was what I was interested in at the time. I was always just interested in the universe, the world I lived in, in terms of just the stuff around me, whether I was in my garden or I was, digging a hole, looking for insects, or whether I was opening up a computer or some electronic device to find out how it worked. So I guess it always started with me saying, well, how do things work? And I realized I was interested in science. I had some personal, well, not struggles, but I was very insecure at the beginning about whether I would be good enough to do science, right? So, there were some interesting things there, but I didn't really let that hold me back. My questions were larger than my insecurity. And so once I got to about maybe 10 or 12, I really kind of realized that was into the fabric of my personality, that I just wanted to ask questions about how the world worked. And I didn't really care if I was breaking status or cultural taboos by asking them. So I was very rude from a very young age. And that's not that normal, I think. And then I went through school and went to university and studied chemistry. And I took a very strategic path to get to where I am as an academic, and I can explain about that. I didn't kind of realize at the time it was a strategy. All I can imagine is I need to get to the position where I could build this team to start asking the questions I really wanted to answer.
Right. Yeah. So you said the path is an academic. I'm really interested in that as well. Because you're pursuing a really big question, the origin of life. And I'm not sure how your academic career evolved, but from what I've known, generally these big questions are not encouraged in the academic path.
Yeah, I think I've always, for me, the big questions have never been optional. They are the reason why I exist in science, right? So doing the kind of more, I wouldn't call it mundane, but easier to sell questions about curing disease or cleaning up the environment or making a new material. That's all fine, and we need that. And I'm not saying that that's not a really exciting thing to do for other people to do, but I am a discovery, curiosity-driven scientist. And so that's my objective. But of course, along the way, I've made some discoveries. So I discovered a system that can produce hydrogen quicker than any other system on the planet. So I thought, well, maybe we'll make a new hydrogen technologies. I discovered a system that could store electrons better than any other battery on the planet, more of them per unit volume. So maybe we can make a new type of battery. And in pursuing this idea of the origin of life, I created the computer, which turns out to be a machine that could make any molecule. and not just, a fantasy machine, but a real machine that works. And I think those avenues themselves could be put out there as technologies, not just for other people to explore, but for maybe to make a company, for other people to get training there. But really, I think the important thing to understand is the question was always driving me, still is driving me, even though I didn't quite understand my own motivations at the time. There was just no question. It was a bit like I found myself at the bottom of a mountain and all I could see was the summit, and that's where I'm going. And there was just no question. Of course, I'm going to the top. Why would I go around the side?
Fantastic. So how close are we to the summit? And let me sort of contextualize this question. The origin of life, there are many theories about it. I think the most famous of it is perhaps the RNA world theory, where RNA molecule self-replicated and it was catalyzing its own reaction. And many theories approach this from a biological point of view. You're approaching it from the chemistry point of view. So what's your conjecture or hypothesis about the origin of life, and why study it from a chemistry and inorganic chemistry point of view?
Okay, the good question. So first of all, about the summit. So where are we on that? There is no, for me, I can see the summit, but I'm quite sure that I won't get there. Now, what I mean by that is not this the origin of life or the summit will be replaced by new questions. There's always new questions. So for me, I think the best place to be on the mountain is about 3/4 up. Okay, or maybe between halfway and 3/4 up, where I can see the top and I understand where I've been, but I'm excited about going to the next place. So that's kind of just to fill that in, because I think for me, it's like a continual journey that I think we all have to understand and enjoy the journey, and making sure we are answering questions with good experiments. And, I think if I was obsessing about being at the top, then I think the wrong type of arrogance comes in. And I think scientists need a bit more humility in the way they ask questions and think they've got to the answers. There are too many know-it-alls right now. And in the world where we have various political problems, particularly with information, that we need to be careful. But anyway, so to your question about the origin of life, I don't really want to ask what about the origin of life on Earth. I want to ask about how life starts in general and how that process is going. And before I explain, I'll preface it to say, look, just imagine, first of all, that humanity had emerged in maybe a few 100,000 years, maybe a few million years from now. If you look up to the sky, I think you wouldn't see as many stars because the universe is expanding, right? Our solar system would be very far away. So you could imagine just looking up in the sky and only seeing one star, that's our sun. And then looking at that star and saying, how did that star start? And everyone obsesses about the origin of that single star. But of course, we are really fortunate to be alive right now, because we don't just see one star, our sun, we see millions of stars, and we still are in the part of the universe where we're able to receive the light to come to us. And so we know that stars are everywhere. That's number one. Number two, if we look hard enough, we know that stars are dying all the time. So if we look in the sky, maybe once every few months, we'll detect a supernova very far away in the universe. And if we look very carefully, we'll see new stars coming into life. So that means that there is the process of star being born, living and dying. Now I think, so for me, the origin of life isn't just about life on Earth. It's like, what is life in general, and where in the universe is life starting, established, and finishing? And I think that it requires not just an exploration away from biology into chemistry, but then into physics and into a new type of science that looks at the science of life. But for me, on Earth, because we can probably suggest that on Earth, there must have been a transition from the inorganic world to a primitive biology, that seems a reasonable place to start. But one thing I should make very clear, although I trained to be an inorganic chemist, My training is not finished there. I'm currently training, in electrical engineering and advanced computational methods. And for the next part of my journey, I don't think that the origin of life certainly isn't just about inorganic chemistry. It's about so much more. But right now, we look at inorganic chemistry, we know that that's not DNA or proteins or information processing in the way that we would conventionally see. So what happens to that material to turn it into cells? And literally, how does sand, as in inorganic stuff, turn into cells, as in biological stuff? And that's, I think, the framing I've got at the moment.
Right. So you're interested in life in general, and the life on Earth, which is the only case we can study right now, is a beautiful example. I mean, it's almost like a handle on the general phenomena, so that we can gain more understanding about the general phenomena. But how do we? I mean, I want to backtrack a little bit, and I'm going to ask you a question that perhaps fuzzy, but you must be getting asked all the time. What is life? How do you define it? Because I think it is important to really put boundaries around phenomena.
It's important to put a boundary around phenomena. I think it's not to be too restrictive. So some people say that life shouldn't be defined and can't be defined. And then people over-define life. And I kind of disagree. I sit in the middle because I'm a practical scientist. So I need to have some kind of labeling associated. Otherwise, everything's alive or nothing's alive. That's not helpful. If we say we can't define life, then by definition, life doesn't exist.
Yeah.
That's clearly incorrect, right? So that's just a cop-out. Then when people say, but life requires this, then you get a political system, right? It's so complicated, right? And then it's like the British, the American, or maybe the Indian political systems, like you need this and this and this. So I prefer to say, well, hang on, look, we will be able to define life one day, but why don't we look at and ask a different question, say, what does life do? And I'll give you an analogy. So say, look, let's try and imagine defining the process of flying or flight before we had aeroplanes. You'd probably go out as a human being and say, well, what is flying? We say, well, there's an insect in the air there, and the insect is in the air and can come down, and there's a bird flying. Oh, and if you're in a particular part of the world, you would see these flying squirrels, which aren't flying, they're gliding. They can jump off a tree, open up their arms, and they have these webs and they can glide, a bit like in a wingsuit to Earth. So you say, okay, flying is roughly using the air to create lift and to move around free from the ground. Okay, so that kind of gives you your first hint of what flying is. Then if you look at an insect and a bird, you can see that powered flight requires you to do work and create lift. So then you fast forward a few depending on where you are from that part of the world, when human beings, what was the first flying? The first flying was the Montgolfier brothers with hot air balloons. I mean, presumably lots of flying have been done by balloons in China and in India and all around, the world, right? Everywhere. Yeah. Then we had powered flight in the US with the Wright brothers. And now I would define flight or flying as the process of getting into a heavier than air object and doing work, creating lift or thrust, and the object in a controlled way moving into the air and being able to go somewhere and then land. So that's a fairly long definition, but it's not kind of like, and you must need wings, and you must need this, and you must need that, because Elon Musk makes, flying machines that fly vertically, right? Yeah. Or try to. So now going to life, you could define life and saying, life needs to be a cell. Life, and then you say, well, what about a virus? Is a virus a cell? You say, a virus isn't alive. And you're like, okay, a virus isn't alive. Well, okay, you need to be a cell. It needs to have energy, a source, and need a waste, and it needs to have information. And then the list goes on and on and on and on and on. And then it becomes a legal document. Too complicated, not helping scientific discourse. The same way, so if you can't define life properly because it's too complicated, and you can't not have a definition, what do you do instead? You say, well, okay, what does life do that non-life does? And that is what I've been focusing on in my work for a number of years now. And I realized that life does something unique that non-living things don't do. And that is that life is able to make in the process of living, it's able to make complex objects that cannot randomly form. And in the same way, sand on a beach can't randomly form a motor car or a Apple iPod or whatever you want to prescribe. So suddenly, if you say, could this be my working definition of life? Living systems are able to take simple raw materials, and through the process of life and information and energy, or whatever life is, let's say simple stuff plus life equals complicated stuff. Then suddenly you have a unique descriptor. And you say, well, then what is life really? Well, life is evolution. It's packets of evolution embodied in small objects. So suddenly you're like, so when people say, is a virus alive or not? You say, no, wrong question. In the same way, I would say, is my iPhone alive or not? That is not the correct question. Is my iPhone part of life? Right. Is the virus part of life? Because you have two strands in life. You have things that are living, okay, and things that are part of life. Well, my iPhone is part of life. If it wasn't for the last universal common ancestor, Luca, evolving into multicellular creatures, then animals, then primates and human beings, there would be no Steve Jobs, there would have been no manufacturing in Taiwan, there would be no iPhone. So this is a perfect signature of life. Now, a virus. Is a virus alive or not? Wrong point to make. Is the virus a product of evolution? Yes. Now, a virus inside a cell is alive because it is replicating in the cell machinery. A virus outside a cell is not alive. Same way for you. When are you alive and not alive? Well, if we sped up a camera and looked at you on a nanosecond time scale, or maybe let's say not a nanosecond, an attosecond, 1 × 10⁻18 of a second, you would not be alive on that time scale. But on a 1 second time scale, you'd be alive. So a virus is not alive, maybe on average, in a week, 1 month time scale, but every now and then when it's in a cell, it's alive. Right. So I think that we have to understand all of that. So my definition of life, or my working operational mode for life, is living systems are things that can take low information raw material and produce complex artifacts that you cannot see, that cannot happen randomly, and that's it. So that's kind of a very simple working definition that allows you to get around all these other confusions.
Right. So when so essentially the process of living transforms things which are low information into complex, high information objects. But does that push the definition just one step ahead, which is in terms of information, and what is high information, what is low information, and isn't information also sort of context dependent? I would look at, for example, a star. What would qualify a star as a low information object, but an iPhone as a high information object?
So that's exactly right. So I will push further now. Now we can talk about information. Information, in fact, is probably the wrong thing. We just call it complicated. So life uses evolutionary processes. Well, life uses machines produced by evolution to make complex objects. That is the canonical definition of life. Now you say, okay, how can I tell if an object has been evolved, like an iPhone, or what about the sun? Is the sun evolved? No. Here's a really interesting thing. You look at the sun is complicated, but it's not complex. It's not, there's no memory in the sun. So the sun, other than the laws of physics that give that memory. So what does the sun have? Well, the sun has a mass, it has a temperature, it has nuclear fusion going on all over the surface, and there's very complicated things happening. Lots of information, lots of data that can be turned into lots of information, but it's not unique. They are the rules governing that the way that information is moving are very simple. There is no hereditary in there. Stars do not produce evolutionary material. The amount of information in our iPhone, by comparison compared to the sun, is trillions of times more, because the iPhone really is the sum total of human technological history. And so going right back to the Stone Age, and then to the Bronze Age, and then to the printing press, and to writing, and to technology, the iPhone kind of had to have all those steps go through over the past thousands of years to get to that object. If you didn't have any of those steps, you would have no iPhone. But the sun works on an 11-year cycle, and where roughly the sunspots get reset. And there's no question the sun is very complicated, but it's not informationally complex. That means I could go to a computer, and this is the drop dead, very simple, sun or phone. I go to my computer, I just type in a few equations, and I can generate a sun. I look at the sky, and I can see that my model and my sun are very similar within most. I go to my computer, and I make a generative model that makes me an iPhone. Impossible. I can't do it.
Right. So it ties back to this idea of compressibility of information, where sun is easily compressible. You can write a small program to simulate a sun, but iPhone, it's just unimaginably sort of, and it'll be a really huge program. I mean, if you see the technical documentation of all the components that build up iPhone, it'll be like pages and pages of stuff. So that's what you're referring, right?
Yes, exactly.
So in that sense, would it be fair to say even this process of life is a continuum? I mean, I can see that sun is less complex than iPhone, but is there an arbitrary boundary where you start saying this is life, this is not life, or is it just big continuum right from the very physical processes to iPhone?
I think it's a continuum, but I think there are useful thresholds. Okay, and I think I think those useful thresholds can be attained in different ways. And I think it's people like to put a kind of absolute value on stuff because people like to do that, but actually I don't think that's not instructive for the individual, but it's instructive if you're doing statistics. So I do think it's a continuum. Basically, life is about getting the universe to create memories of itself. So the sun doesn't really create many memories of itself. It's just like it uses the fundamental laws, does fusion, and again, its mass changes, its composition changes, and so on. Because the energy is so high, everything is mixed and so on. Whereas if you've got on Earth, because you are able to create small changes over time, and those changes weren't forgotten, those small changes could affect the future in a causal way. That chain of causation is what gives you the continuum that gives rise to biology. And before you know it, you have a living cell. And so that continuum goes through different speeds, right? The universe evolves at a certain low rate because it requires on mechanical interactions. But then suddenly when the universe invented the molecular machinery that you find in the cell by evolution, then suddenly when they came together, it sped up dramatically and got faster and faster and faster. So those speed increases, although they are smooth, are steep. Right. And so basically what you can view is they've got a continuum from here to here, but it's kind of flat, 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 whoa, and then up. And I think there are three kind of regimes. There is the statistical regime that we have in physics. We have and then we have the transition from the statistical to the biological in chemistry, and that's genomic. And then we have the transition from genomic living to technological. And what that means is the probability function is just compressed. So physics, you have a nice wide probability function of all the processes. Biology concentrates that because you sequence information. Technology makes that even narrower. The variation on things, if you look in the iPhone at the transistors and so on, they're identical and there are billions of them. Whereas in a living organism, you might have a lot of hemoglobin, protein, but there will be, you know, defects in the protein, oxidation, mutations, and so on across biology. Even though it'd be pretty good, but not perfect.
So the preciseness of information keeps on peaking as life evolves.
It seems so, doesn't it? Yeah.
Yeah, that's interesting. So, how do you take that insight and then find alien life made of inorganic materials? You write that on your homepage. You're interested in finding inorganic aliens. How do you go about finding them?
So a few years ago, I developed a new theory called assembly theory, and assembly theory is a bit more internally consistent than entropy. The concept of entropy is something that human beings impose upon a system, you know, once you know all the information about a system, it doesn't have any entropy really, because you know all its information. Yeah. So entropy is really just a construct that says what is your lack of information here? How much information do you not have? And that's good for the human being looking at things and looking at physical processes and looking at statistics, but it doesn't really help us understand how evolution works, because we don't quite understand the causal chain of information. I've been struggling for this for a number of years, as has all of humanity. And I decided to build a new theory to say, okay, let's not worry about entropy, but look at how, given us an object, whether that object is an iPhone, a cell, a beer glass, a pen, or just a sandcastle, how likely is it that that object could have been spontaneously formed without any compressed information, you know, helping it unfold? Some evidence of evolution. And so what assembly theory does is it takes an object, you look at the object and say, right, what is my basis set? What are my pixelization? So let's say it's a sandcastle, and you look at the sand grains. Yeah. And say, right, okay, how many sand grains are needed in the sandcastle to organize it here, here, and here? And then what you do is you take your pile of sand and you turn your pile of sand into a sandcastle. But you don't do it by, you do it by basically double it by looking at the fragments and increasing the fragments. And every time you increase the fragment by a certain amount, you then put in a unit of information and you look at that. So you say, okay, let's say I've got a sandcastle that is just a really simple, it's a picture of a house, right? Let's say a classic UK house. It has a roof, you know, a triangular roof. It has one door. It has some windows. Okay, once I've learned how to make one window, I can make the rest. So there's information in the window, and if I have two windows, that's another piece that just doubles that information. 3 windows is just 2 more units. So what I do is I compress that information down, and I say, what is the minimum number of random moves that would need to be made to generate a house? So it's a bit like, you know, in an ordered set. Then I say, okay, how likely is it that number of moves could be made randomly if the sandcastle house needs 1,000 moves to occur with perfect registry? Then the likelihood of getting 1,000 moves with a perfect registry is 0, right? It's very low, if not 0. It's like the same way of saying, okay, I need to roll my die and I want to roll 6 sixes. So what is the probability of rolling 6 sixes in a row? Well, it's 1 in 6 times 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 1 in 6 is really low. What is the probability of, you know, just throwing 1 6? Well, it's obviously 1 in 6. So so if you suddenly see an object that required you to roll 6 sixes one after another perfectly, and you see it happening, first thing you do is you question your die. Is the die loaded? If the die isn't loaded, you say, well, something is happening here. There must be extra information. Yeah. And so what assembly theory does, it allows you to identify objects that can't randomly form. So now I tell you, look for inorganic life. What I do is I now say, okay, is there an experiment I can do in chemistry that allows me to find that. And there's 3 experiments I can think of very easily. There's one called infrared spectroscopy, where infrared is basically looking at the color of a molecule, but it's not just the color of paint on the molecule. It tells you about the number of parts in the molecule. So basically, the molecules move in the infrared and they move around and dance. And when each part of the molecule takes energy, it dances in a different way. So a molecule with 3 parts, crudely, this is not mathematically correct, but roughly okay. A molecule with 3 parts would have 3 colors in infrared, 3 moves. A molecule with 10 parts would have 10 colors in the infrared. A molecule with 20 parts would have 20 colors in infrared. So the more the number of parts, the more complicated the object, the more it must have been made by evolution. And so I've made a detection system that can be used in space and in the laboratory to go and find living systems using this approach.
Okay. So just backtracking a bit, I'm trying to understand the assembly theory. So it's essentially trying to trying to sort of recreate the program or the path of steps that's needed to construct an object. So in that sense, I was curious. I mean, A, it sounds hard. I mean, in the computer science terms, it sounds NP hard. How do you come up with a program to construct an object? And B, if there's a sand castle or there is a pile of sand, how do you distinguish between these two? Because the precise locations of grains in both of these objects, I mean, they're quite precise, right? So what distinguishes one from the other?
So first of all, what assembly does is probabilistic. So it doesn't tell you how assembled the object was. It just gives you a minimum threshold to say, to make this randomly, you needed to do 10 things perfectly in a row. So that's the first point. So it doesn't really make any decision about how biology did it or not. Second point is, whether you're looking at sandcastles or molecules, you then have to change your frame of reference. If you're looking at molecules, your assembly space is made up of atoms and bonds because you add them together. If you look at sandcastles, it's sand grains. Okay, and then you can then say, I'll take one sand grain, then I double it, triple, then I double it again, double it again, double it, and very quickly you have a big sand block. But of course, in the sand castle, you can say, oh, hang on, my feature space doesn't go down to a sand grain. It's to a cube of sand. So I don't need to go all the way to the sand grain. So what you can do is by looking at the image, you can pixelate your image and say, so what assembly theory is, it's like zip compression, but with an ordering in time. Okay. So like now if I'm going to paint my sandcastle, what is the minimum number of paint strokes do I need to do to make it? Given that when I've made one pixel or one object, I can reuse that for no cost. So I'll say that. So I'll say that again. It's like I take my picture of my sandcastle and I say, right, I'm going to paint this with a minimum number of steps because when I've done one step, I can use it again at no cost or very minimal cost. So it's like a reuse. So that's really important concept to kind of get across. And so you don't have to go down to sand grain. You can go to cube. So what you do, you have to look at your object and say, what does my object get divided into? And I think that's a very important thing because it is an NP hard problem. But fortunately, the threshold which things start to get really interesting is before NP hardness in almost all cases, right? Because I can show you that if you even have an assembly, so when a molecule, any object has an assembly number greater than about 10 to 15, you know the chances of that happening randomly is basically 0.
Right. Okay, understood. So applied to sort of this, I mean, on inorganic aliens, to detect them, you're essentially looking for signatures in the infrared spectrum to see if you're able to find
infrared or mass spec, or even optical images.
Oh, even optical images.
Yeah.
So what signatures do you expect to find in optical spectrum?
Well, it depends whether you're going to an alien planet or you're looking at using a telescope, right? And I think that's really hard. But what you could do, let's just imagine we're taking lots of photographs over all the exoplanets, right? Let's just say, imagine it's 100 years later and we've got telescopes to an imaginable resolution that not only can we find exoplanets using the transit method, but we can get some spectroscopic data. Now, what we can do with assembly theory is we won't only just gather spectroscopic data that tells us something about the composition. If we look at the variation of that data, we can build a statistical model about how likely it is that these planets have some kind of random processes going on, or is this very simple planetary phenomena, or there are phenomena that need more degrees of freedom. And so what assembly theory can do is count for degrees of freedom, whether it's likely that these processes are going on. And we should be able to see remotely these things happening. Now, in optical images, the really important thing, if I brought you a painting and say, right, here's my painting, I don't know what art you like, and it's very culturally specific. Let's just say a painting. But here is a painting that was done by a famous artist, and a painting that was done by a child, not just painting. How can you tell the difference? Well, if you've only got one example of the artist, it's very hard, right? And if you've only got one example of the child, it's very hard. But let's say now I'm going to give you 10 paintings from the artist and 10 from the child. Immediately with assembly theory, you'll be able to tell the difference. Because what you can do is you'll look at common shared constraints in the artist's brushstrokes. Say, okay, there is what I'll do is I'll add all the paintings together and compress them together in one line, and then I can then use and then divide it up to look at changes in that and look at the assembly space. Then I'd get the child's one and do the same, and then I would have my ground truth, like how many steps. Then I could use machine learning, just basically computer vision machine learning, to then see if I could then train a neural network. And then and this is a beautiful thing about assembly theory. Assembly theory can give the ground truth to machine learning, because right now machine learning is just regression, and it's just regression without the coefficients don't mean anything. But if I can do what's called portable machine learning, I can learn on one set of objects, and then I can use that learning algorithm or that data set on another set of objects, and then still use it and start to aggregate in knowledge. Then suddenly there's something very profound going on, and machine learning then takes on a deconstructive role that isn't just curve fitting.
Right. So just to summarize what you're saying, and is my understanding correct? I mean, in terms of exoplanets, if you take, for example, maybe thousands of exoplanets, optical features, infrared and mass spectrometry, you may try to sort of cluster them in terms of their assembly, sort of the metric that comes out of this assembly theory. And if there are multiple sort of clusters, something interesting is going on in exoplanets.
Yeah, so I think that one of the things I should mention in assembly theory, the assembly number tells you about how improbable something is. There's something very exciting that goes on with that, in that what you look at, you have to bring in the abundance of the objects undergoing that transformation. So it's always possible that if you find one object that looks really weird, right, it's just naturally occurring. It's unlikely, but if it only has an abundance of one, then the information associated with that object is zero, right? But as the abundance of that object goes up, the more complex the object, the more information content you have. So it's very important that I make that comment to say not just about individual objects, but the abundance. So the number of examples, because those rules have to be used again and again. And if you can apply that heuristic to clustered data from exoplanets, of course, with mass spec, you have to actually get to the exoplanets, so that's probably impossible right now. But certainly with spectroscopy, you can infer, and with imaging, you can get proper information. You can then start to look at the population of processes across the universe, and then you can classify them and look for structure. And I'm pretty sure that in the next 100 years, we will find life all over the universe using this method. And we just have to get our heads straight and understand the theory and understand how assembly theory identifies evolutionary dynamics. And one of the things that we have to do in our own laboratories is make our own life forms and show that how we go from evolution. Because if you take one of the things I was saying a few moments ago, like this is impossible, then you're going to say, well, okay, you're just not invoking intelligent design. And that's a really important thing to talk about, because no, I'm not saying it's impossible. I'm saying assembly theory allows you to identify things that have got there through evolution. Then the next question we have is, how do objects that have no information in them create their own information? That question is answered by one word: evolution and selection. Okay, so evolution is one word, selection is one word. You can both use them together or separately. Probably selection together gives you evolution, but it doesn't matter.
Right. So I'm still trying to get a really good hang of it. I was thinking of an analogy. If we are trying to sort of take a picture of a beach from very far away, and we take a number of pictures as we move along our telescope, there's sort of grains of sands, and we have multiple pictures of it. But if one of the pictures we see a sandcastle, I mean, that's, say, an exoplanet with life, as an analogy. How would we identify that one picture with like a sandcastle apart from all the other pictures, which are just grains of sand?
Yeah, so what you have to do, analogy, is you have to make sure that you have you're going to have a whole population of photographs of sandcastles on all the planets, right? Lots of different sandcastles. Then how do you say, well, how are these sandcastles not just naturally occurring features? So what you have to try and do is identify information. First of all, get lots of data, lots of instances of the same exoplanets, but with different features, right? Okay. Showing with memory in them. And you just need to show that there are more variables controlling these features than there are than a certain threshold. So, because if there's more variables than a certain threshold, you see this in abundance, you'll see the whole process of evolution occurring. And that seems really hard, right? Because people right now, human beings, keep confusing random with complex.
Yeah.
There is no such thing. So complexity is a bad word. In fact, if I could destroy a word, I would destroy complexity. Because what we mean by complexity is we mean one word. Well, we mean one process. We mean evolution. Evolution generates all the complexity in the universe. Complexity does not exist without evolution. Things are complicated without evolution, but they are not connected. What connects everything in the living system that's complex? Evolution. I think once we flick that switch, when we look at the exoplanets and we look at all the complexity and we realize that complexity is actually evolution, we can then start to then analyze that data and see where those free variables are. And the question is, at a distance, using telescopes, will we get enough information to unambiguously assert that we are seeing evidence of evolution? And that's what we have to study right now. I'm not 100% sure, but if we can get more and more data and higher resolution telescopes, I think so.
Right.
And I think probably we are contributing to another alien, extraterrestrial search elsewhere in the universe. They can never get to us because the size is too big, right? Yeah. Interstellar travel is probably impossible, right? Really, any realistic, but we will know that we aren't alone. Right. And that's a very important starting point.
Yeah. So in some sense, I mean, if an alien was studying the solar system and they point their measuring apparatus at the Earth and Mars, there will be many more variables that have to account for what they observe from Earth versus Mars, which would be simpler atmosphere, and Earth would be all sorts of complicated gases, dynamics of gases, reflection, satellites. So many things would have to be accounted. So that's what you're saying is a mark of complexity, the word you want to ban.
Yeah, exactly. Okay. And I think that's a really interesting thing to kind of start to, some complexity theorists out there misunderstand complexity. All complexity in the universe is produced by evolution. There is no complexity that's not produced by evolution. Once you realize that, suddenly the switch flips, and you can re-see the universe.
Right. So coming back to what you're trying to do in your lab, specifically with computer, and maybe computer is a step for sort of progressing to answer how life started on Earth. So do you have, I mean, this seems an improbable step, having inorganic chemicals to becoming self-replicating systems. So do you have an overarching framework to sort of at least try to understand how this might have happened on Earth specifically?
Mm-hmm. So we have three things we're trying to do. The first of all, well, it's four things actually. I don't think it's improbable. I think that evolution can happen all the time in the universe. It's simple. And I think that there is this transition, right, where we get more and more evolutionary complexity. Let's say evolution complexity. And it isn't, so I keep saying, oh, it's really hard. And then I say it's really easy. Well, what I mean is the way to get from no life to life, the process is selection. So evolution is the process of selection over many and many cycles. And that causal process gives rise to the evolutionary dynamic that we see. So what we need to do in the laboratory is say, okay, I need to do a chemistry experiment and I need to do it many times. I need to look at differences between each cycle. And those differences we will see selection, and in the end you'll get to evolution. And I think now I always fall into big traps. I'm now 47 years old. I've been dreaming of doing this for more than 40 years, right? Since I was a child. For the last 20 years, I've had the capability of, well, let's say for the last 10 years. For the last 20 years, I've been an academic now for almost 20 years, okay? Next year, it'll be my 20th kind of academic anniversary since I was independent. And during that time, I built my team up from kind of doing inorganic chemistry to inorganic chemistry, organic chemistry, robotics, computer science, machine learning, mathematics, electrical engineering, okay, and biology. So like 8 disciplines all in one team, all working together. So in the last 10 years, we've been trying to build the technologies. So the computer technology for automating chemistry. We also need an analysis technology, and we need the theory. So I've been building all this together. Now, why? Well, let's think about how physics works. How has particle physics been so successful? Well, you have the standard model. The standard model allows you to then make predictions and make a simulation and say, right, these energies, I expect these particles and they have these features, okay? Then I can then go and build a machine with a detector, and then I then go and run the machine and I look for the anomalies that I get. So now think about it. What is my standard model of biology? Biology is selection. Selection works and gives evolution, and evolution generates information from nothing, from time. So I know my standard model of life is selection. If I then apply that over time, I get evolution. I now need to build a machine to do the evolution. Now I need to use assembly theory to see when my machine is producing high assembly objects from sand. That's what we're doing right now. And so it's really exciting because all those elements have come together in the laboratory. If I can make life forms, or if I can see evidence of selection in the lab in chemistry and then accelerate that and get towards open-ended evolution, then I think that will be really exciting. Will I manage to get all the way? I don't know. I don't know how fast it will be. But all I know for sure is that we'll be able to do it. In fact, we are seeing hints of it right now in the lab. We have data that suggests that selection is not only possible, it's happening. Now what we need to do is to see how that evolution is manifested. And it's happening right now, not in 5 years, not in 3 years, but in 1 year.
Okay. So you're starting with chemicals, basically sand or inorganic chemicals, and then you're observing how these chemicals evolve over a period of time to produce more and more complex patterns and chemicals, which wouldn't exist unless there is a process of selection happening.
Correct.
Okay. And you said you've made progress. So how far are we in terms of really kickstarting another branch of life on Earth in your lab?
Well, I think we're pretty close to kickstarting another branch of life on Earth. Like all the other branches, it will be dependent on, well, like most of the other branches will be dependent on the one before. So, I'm creating it. In a way, the critics can say, hey, well done, you made a life form, but without you, there'd be no life form. But if I say, oh, but hang on, my simulator is to try and remove me, but just to organize, to simulate the day night cycles on Earth, the year and all this stuff, to have cycles of movement. That's what we want to try and be able to do. So I think that we are in a situation now where the machinery is working. I've written the programming language for chemistry. I've got the hardware, modular hardware running, and we have 3 chemical selection engines, which we call them, in the lab right now. And they're working at 3 levels, one at the molecular level, one at the polymer level, and one at the cellular level, making artificial cells. And we're just seeing what happens. And we're looking for evidence of selection in these cycles coming out. And I think that will really start to nail down some pretty big questions.
Right. To put a critic's hat for a second, if this transition from chemicals to what we have as full-blown cells were to be common, as you're saying, shouldn't we find multiple branches of life instead of just one that we have, the DNA-based life? So
I think that I don't know is the answer. And let's think about how evolution works. I think that the life that we have on Earth is, first of all, uses all over the entire planet. So we don't really see anywhere on Earth where there isn't life. So it was a planetary transition. And I think what we show is that in the end, you probably did at the beginning have lots and lots and lots of different life forms occurring, but they were very simple. They couldn't really get a very big memory. And only by cooperating and searching the space of all available chemistry could they become to the best solution for evolution working on Earth. Now, there are some exceptions to that. If we go to environments on Earth which have been separated from one another for 4 billion years, right, or so, then sure, we should find other life forms. But I don't think that life on Earth life has been everywhere. It's very promiscuous. So I think with that promiscuosity, if that's a word, promiscuousness comes the planetary phenomena. However, that doesn't mean that in my lab, if I keep it isolated and I simulate the beginning again, that we can't get on a new track. And would it be interesting if we get on a new track that's similar to what we have already, but maybe has, 25 amino acids, or let's not say 25, but let's say 26 amino acids, and doesn't have 4 base pairs, but has 5 base pairs, right? Or maybe less, I don't know. There's good mathematical reasons for making things quadratic, but let's see, how you go from the quartets and the triplets that you see in biology now to other units, right? Because this is error correction. But so I think that it is reasonable that you might see lower down at the very roots of the tree of life other chemical processes that could have gone into other types of life, and that basically there was a competition and there was a series of winners, and those winners ultimately manifested in Luca, the last universal common ancestor, of which contains RNA, DNA, as we now see it, in proteins and metabolism. But I think the major misconception is that RNA is somehow foundational in life. It is not. It is easy to show on a piece of paper that RNA has nothing special about it that gives its rise to life. There are many other solutions to the emergence of life. RNA is an elegant solution. It is a highly sophisticated one. It was well searched for, but RNA wasn't the start of life. There was something below RNA.
Right. Sorry, what did you mean it's easy to show on paper? How do you go about that?
Well, so what you do is if you take the formula of RNA and take the base pair and then write down the formula and then draw a graph of the base pair, you can then also draw from that formula loads of, allow the formula to vary slightly, draw lots of other base pairs, that are different, but still have the properties required to undergo evolution. And that people were saying, that RNA is really perfectly evolved for this one thing are wrong. And the reason why they're wrong is there are other objects out there that are equally good enough. Now, what people out there might be saying is like, taken this history, RNA is the answer. That is correct. I don't know if you have what your favorite computer is, how long you keep your laptop for, but I'm sure you like your laptop. It has scratches on it, probably has stickers on it, probably. Those stickers, those scratches you put on yourself. They're yours, right? That's your computer. That doesn't mean to say if you've got another computer and start it again, you put different stickers on it and get different scratches. That doesn't mean that only computers can have that configuration of stickers and scratches. And I think that people get really confused by this causal process.
Right. So, as you were speaking, I was wondering, now we've sent rovers on Mars to find out life. So do you have any hopes or expectations whether we'll find life there? And if we find it, I'm assuming you would expect it will be a different branch or a different type of life, or?
So I think there are 5 or 6 possible scenarios. Number 1, they find no life. Number 2, they find just the life that we brought from Earth, and it's exactly the same. Number 3, they find life that looks like it's Earth-like, but they rule out contamination. Number 4, they find similar to Earth-like life, but there are differences. Okay. 5, they find a common mineral organic origin of life that kind of maybe could have seeded life on Earth. And I think that's probably would be interesting. And I guess the last one, if Mars isn't dead, they find a weird life that we didn't expect, like a really inorganic life that maybe was a foreign precursor to life on Earth it's been long since lost. And it is interesting. I think that Mars looked like it was habitable before Earth, whatever habitable means, but it means that selection chemistry could occur on Mars before selection chemistry could occur on Earth. So wouldn't it be interesting if selection chemistry kept going and started to find some interesting ways of evolving, and those evolutionary entities were ejected from Mars by asteroid impact and made it to Earth, and then seeded Earth's complexity, gave Earth complexity at the very earliest time when there wasn't complexity possible, wasn't selection possible. And then as the Earth was cooling down, and then selection and was able to start. And maybe Mars gave Earth a head start, and that was just a part of the search space. But they are all possibilities. But I think that I don't know if Perseverance is going to find life. I'm not sure it has the right equipment to find life, but I'm going to be excited to see what the interplanetary scientists find.
Right. So talking about Mars and Earth and talking about solar system in general, it seems, intuitively it feels some planets, most planets are sterile in the sense of these selection, evolution, even on the chemical level, probably is not going on right now, while on Earth it was going out. So within the broader definition of life as a process, have you characterized what minimum viable conditions have to be? And I'm not talking about specifically what existed on Earth, but what has to exist for life as a process to kickstart?
Yeah, I think that's super important. I think that if we're going to assume that life, I have my biases, right? My biases are as a chemist, my baked-in biases are you need time. Not a lot of time, but just time as a process. Lots of physicists don't understand time, and I need to put time in explicitly. You need the ability to make and break bonds, right? Molecules. And you need some energy, and you need an environment that allows those bonds to interact in. So there's some kind of selection. So they're the minimum things. Now, I don't know if most of the solar system is sterile or not. The moon is certainly sterile. We've been there. We've found nothing on the timescale, at least, that we've been looking on the moon that there's any evidence of life. And the assembly number of the moon is low. It's below 10, right? Apart from the human objects on it. And there's reasons for that. Why is the moon a failed object in terms of life? Well, the gravity is low. The composition of the moon seems to be very, very limited, and there hasn't been much ability for. There's been no energy source and physical manifestation of that energy source for selection. So then you need to look at other places in the solar system where there's stuff and energy and potential for selection. So Venus is interesting. I'm sure selection is going on in Venus. I don't think Venus has microbes on it in the same way that the people were saying with phosphine. I think that's not necessarily right, but let's not worry about that. Venus is hot. There's some solid, there's stuff moving around. Could there be life on Venus? It's a good question. It might be that you might need a triple point. You might need solid, liquid, and gas coexisting together. And because Venus doesn't really have any liquid water or any liquid on the surface to speak of, that might not be enough. But Venus is interesting. Titan is also interesting. It's colder, but it has, again, all these bonds and so on. Europa is interesting. Enceladus might be interesting, but it's a bit small. I think Enceladus might be a bit like the moon, but I don't know. I haven't been there. There is reasons to be excited about Enceladus. Saturn and Jupiter might be too harsh, right? Bonds aren't really formed. It's too crushing, too intense, And so I think that the bottom line is we need to go to every object in our solar system and survey it for life using not astrobiological constraints, but my very simple, is there selection? Is there evolution? Is there, therefore, complexity? So what you need is the three things in order: selection, evolution, complexity, in inverted commas. Right. So, because what I really mean is selection, evolution, and assembly. They are the three things of life, or the pathway to life.
Right. I hear you. My interpretation is that this process of life might be much more common than what we've assumed if we think about it right from the chemical level. But after that, once there is a chemical life going on, shouldn't the process of increasing complexity increase? But we don't see that. We don't see, Europa, Titan, everywhere else, we could have seen, if not intelligent life, but something bigger than chemicals. But I think we clearly haven't seen that. So even if chemical life exists there, what stopped increase in complexity from there on?
Well, I think we just don't know what we're looking for yet. I only invented assembly theory in the last 5 years, really. And that's reframing the way I look at everything. And understanding that we have a continuum for life is really, I think pretty mind-blowing. I think that there's life everywhere in the universe, but there are different potentials for life to turn into, there's selection everywhere in the universe, but there's only limited potential for open-ended evolution. And open-ended evolution is really needed to establish life. And then once you've established life, then there is a road to an ill-defined road to intelligence, if you like. Yeah. And I just don't know what that looks like, and I'm not sure if we would even recognize it. Would we recognize it if Venus was alive with intelligent beings? It's not even obvious to me that we would recognize it.
Yeah.
How would that be? Intelligent beings, okay, if they were like us and had spaceships and so on, we'd see them like launching up and might even come visit us. But what do we actually even mean? If Venus had dolphins on it, swimming around underneath, right, like we've got on Earth with dolphins, which are arguably intelligent and arguably alive, how do we know? So I just don't think we actually even know enough to really correctly answer the questions about whether our solar system is alive or not. And I think that's really exciting. I guess for what I know, if I'm not going to throw away all the assumptions I was born with or developed along the way, I would seem reasonable that Earth is the only planet in the solar system that has open-ended evolution. But there may be a few candidates where evolution is starting to happen, but it's just limited by happenstance. Then we look further in the universe. I think the Fermi paradox is wrong. I think Fermi wasn't thinking properly. If Fermi was thinking about assembly, probably there will be no Fermi paradox. And I think we might find in the next few years that we see life is everywhere in the universe.
Right. So switching gears a little bit, you're making this computer to simulate, not simulate, actually do chemical reactions at scale. Why not pursue a digital sort of strategy? I mean, if it's about information, uh, you could simulate a lot of this on computers as well, right? And I don't know what's the state of simulating quantum mechanics, but can these chemicals be simulated on a computer and you just accelerate this process by several orders of magnitude?
So this is a really interesting question. I think there are lots of people that misunderstand the power of computing, right? If you think about it, what you want to be able to do in the lab is simulate literally countless trillions, if not quadrillions of molecules that are likely to become informational, self-replicating catalysts for themselves. Now, the problem with a computer is the computer can only do what you give it. So you can say, here's a budget of atoms, here's a budget of experiments, and the rules you give it, the data you give it, you already know from chemistry. But what about unknown rules? So you say, so it's okay, given that we invented the rules of number theory, it's okay to give it to a computer and say, just go and generate all the prime numbers forever, right? You could go and do that. But you can't say to a computer, you're going to go and generate all the molecules forever, because that problem is super NP hard, like unimaginably hard. And also, I don't think it's relevant. And I think that it's probably cheaper to do the physical experiment and generate like a mole of molecules, 6.022 times 10 to the 23 molecules, rather than put it in a computer.
So
I think the problem is our computer infrastructure is easier for us to just write a program than build the robot. Sorry, you were going to say.
Yeah, I was saying in some sense you're using the universe and the physical stuff as a computer. You're having the world do.
That's the question. When is the universe a computer? When is the universe not a computer? I think the universe is a computer when it can simulate itself. Mm-hmm. And the universe and I have a very interesting answer to the simulation question. The universe we cannot be living in a simulation.
Okay. Why?
Because there is not a resource to simulate ourselves. Now, people might go, but you're living in a simulation. There's a bigger universe out there than you. And so therefore, you don't know that there isn't more infrastructure. I'm like, yeah, okay, but that's fine to some degree. But you have to answer the question. If I'm living in a simulation, the universe that I'm living in is at least as big as me, if not bigger. So there is still a universe. It's a bit like, it's a recursive problem, right? It's a cat. So people say, how do you know I'm not in a dream? Well, okay, if you're in a dream, fine, I could be in a dream. But how is that dream? That dream must exist somewhere. So then let's look at the likelihood. Either I'm in a simulation and the universe is even more complicated than I think it is, fine. Or I'm living in the universe and I'm able to control parts of the universe and do simulations within it. And so, it doesn't actually help me, does it, to say I'm in a simulation? And I think Elon Musk's argument that it's more likely that we're going to use simulation is actually incorrect. Because I think the nice thing about the universe, the way we understand the second law, is that the universe is not itself simulatable. Because there is not enough resource. You would have to make a computer at least the size of the universe to simulate the universe. But then after 1 unit of time goes by, the universe is infinitely bigger, not infinitely, it's a lot bigger again. So then to simulate that universe, you need to build a computer the size of the universe again. You have to keep doing it. Every time the time goes forward, the size of your computer needed to simulate the universe, it increases. Therefore, by application of Occam's razor, I can fairly confidently say we are not living in a simulation. That doesn't mean we are not going to be living in a simulation in maybe 100 years, but we're not right now.
Okay, so coming to the applications, I mean, you talked about that on the way. You've helped actually solve some practical problems as well. So, computer is a critical element for discovering how life might have started, but what else is it good for as well?
So when I built the computer and I realized we had to have digital control of simple chemistries, I wondered if it would be possible to have digital control over more complicated chemistry and do chemical reactions and make drugs. And actually, that's what the computer actually now does. I have more computers in my group making drugs than I do doing origin of life. So there's about 16 computers in the group. 12 of them are making drugs and doing organic chemistry. And what I realized is that when I built the origin of life computer, I could build a chemical state machine that could do a thing called computation. So let me just define to you computation. Computation is the process by writing a program and running that program on some hardware, and that program will do a certain thing. And a computation is universal if I can do it on any qualified hardware. So if I wrote a program to order numbers between 1 and 100, random numbers up to between 1 and 100, I can run that conceptually on any compatible hardware, thanks to Turing machine or the Church-Turing thesis. So then I thought, hang on, is there chemistry? Can I make an abstraction of chemistry that allows me to make molecules on any qualified hardware using a code? And the answer is yeah. And what chemists have been doing for years is doing things in a traditional, bespoke way, not precisely recording stuff. And therefore, not all the chemistry worked all the time. And what I've been finding with a computer is that once I write the program will always run on the qualified hardware forever. So really, computation is identical to computation, and computation is also Turing complete. That is, that computer code will always run. It is a universal truth I found in chemistry by getting the right abstractions of the synthetic chemistry. So now we're designing robots that you can program to make any molecule that you can imagine that's physically allowed by the laws of chemistry in the lab.
Right. And can't you use your assembly theory to reverse engineer any chemical and then make it?
So there is in chemistry, there is a very nice theory called retrosynthetic analysis where people use that to retrofit. And what retrosynthetic analysis is, it basically knows the current practical laws of chemistry and allows you to break big molecules into smaller ones that are practically possible. But of course, assembly theory is related to retrosynthetic analysis. But when you tell chemists that, they get very upset. Okay, and so there's a big cultural barrier, right? Because retrosynthetic analysis was invented, maybe 50, 60 years ago now by Robert Burns Woodward, I think, him and his contemporaries. And they were fantastic chemists, and they realized that organic chemistry is a really sophisticated game like chess. And once you knew the rules, you could basically move around that space. But what Woodward did, which was beautiful, is that he combined his knowledge of chemistry in terms of the abstract knowledge with the tacit knowledge in the laboratory of what reactions are possible. He made that connection. But that connection has always been kind of cultural in chemistry and has never been programmed. And I am completing that process with the computer, with computation.
Right. I mean, I can imagine far in future, you could just describe what sort of property do you want a chemical to have, and somehow it reverse engineers, and maybe you could describe it just in plain language.
Yeah, not in the future, we can do it right now in my lab. We have a project running called The Artificial Chemist, where you describe a property and it spits out not just the molecule, but the code to run on the robot.
Right. That's amazing. So can anyone, is it only available in the research setting, or are you pushing out?
I've started a company called Chemify. Chemify is aiming to do to chemistry what Spotify did to music and Google to the internet and all this stuff. We're just starting a company, but really the idea of the company is to get the foundation of computation out there. And it's very early because there are hardware, hurdles and things like that, but we're getting there.
So going forward, you imagine this computer to be distributed all over the world, and literally chemicals are just beamed over the internet.
Yeah. And more importantly, it won't be just my computer. I have shown that computation is Turing complete. So everyone kept saying to me, "Oh no, you're going to compete with chemists. Chemists won't adopt your computer. They won't adopt it." I'm like, no. I've already what I did. My trick is I adopted chemistry, okay, using computation. And so what that means is any robot ever made by any chemist in the future will be compatible with the computation. Otherwise, because computation is universal. It's a bit like people saying, oh, I'm going to make a non-Turing complete computer. It's like, why would you do that? That means the programs you make are portable, they wouldn't run. It's like, saying it's kind of silly. So I think that the only way to disrupt chemistry as a culture and a discipline is just to make sure that the KDL chemical programming language I've developed is compatible with everything. We'll make sure that everything can run. And it's basically, there's a hardware connection because, there are companies in the UK, in the US, in China, in India, in Japan, Korea. Lots of countries are making their own special robots to do materials discovery and chemistry. But what they don't realize is that my robot, my way of thinking, covers them all.
Right. So with something like this, I'm just curious, what's the reaction of the chemists, especially in the community, because it could disrupt what they've done. I mean, essentially, this could open up the hacker culture that exists for software to be in chemistry as well. And probably you'd no longer require such long specialization, academic specialization.
Well, I think the specialization of the chemists will have to change, right? Chemists will have to evolve. I think that to start with, people just told me it was impossible. And I just ignored them. And then as I showed them it works, they all said it's obvious, and then suddenly everybody's doing it. But because they're not universal, they don't have a universal workflow. I think that as things get more universal and connected together, then the skills are going to shift, aren't they? From practical skills that you no longer need to have to more types of computational informatics skills. And as chemistry goes digital, it will open up everything because not everyone will need to be in a lab. You'll be able to simulate it and validate the molecules in the same way you could design a new circuit now and simulate it without having to make it. Right.
Great. So thanks, Professor Lee Cronin. This has been an absolute pleasure to talk to you, and hopefully in the coming time we'll hear news from your lab where you've kickstarted another branch of life. That'll be super exciting.
Well, it's very nice to meet with you and have the opportunity to talk to you and your podcast listeners through this podcast.
Thank you. Bye-bye. Take care.
Thank you. Bye-bye.